Bonjour, mes amis. Nope, French did not page in. All right. Welcome back, .NET API review. We have a whole lot of red, and I'm guessing we're going to get through half of one of them. Because today we are talking about Tensor T and supporting types part 2, issue 103611, and let's grab the scroll bar and let's see how long it is, and we'll keep going, and we'll keep going, and we'll keep going, and we'll keep going, and there's no way we're going to get that far today. But let's see what we can do. So, Tanner, you're up.
Yeah, so to start with, thankfully, a lot of this is similar to things we've reviewed in the past, so that those parts might be faster to get through. No promises, though. Uh, this is a continuation of the previous API reviews around Tensor, TensorSpan, and the supporting types. Um, the first thing in the list is just that C Sharp 9 has a feature that allows you to use unscoped ref in interfaces now, which means that we can actually fix the iRead-only tensor interface to do the nicer thing and return the read-only span directly, and still have it implemented by the types we desired. So it's just saying that we should change it from the void getLength method to the one that explicitly returns the buffer. Uh, that way users have a nicer experience with it.
And just so that I know what we're talking about when we go forward, the the purpose of that feature is all implementations are also required to say on scoped ref there.
Uh,
Like it's contagious.
it's uh, so it's the interface. Anyone accessing from the interface is presumed that it might be tied to the lifetime of the struct. But a class unscoped ref can't be specified anyway, so it doesn't exist for classes implementing the interface. And a struct implementing the interface that didn't require it to be unscoped ref could leave the annotation off if they were not tying it to their own lifetime. So someone accessing the member directly on the concrete type would see it as normal, and someone accessing it through the interface would see it as unscoped.
Okay, that actually makes sense.
Yeah.
So the interface is the most conservative declaration.
Yes. That second one should be strides, though. It shouldn't be lengths.
All right. To be very clear about the first feature to begin with, it means like when I call read-only tensor.length to get read-only span, the that I can then continue using it after the current method completes from like
No,
outer.
the
Okay.
the opposite.
The
Yeah. So
opposite, you
so
cannot. Okay.
right. So normally any span or ref returned from an instance method of a struct is assumed that it is not tied to the lifetime of that struct. And
Okay.
so therefore it doesn't contain a byref to any field within that struct. Unscoped ref basically flips that and says, now I am tied to the lifetime of the struct. And as soon as that struct goes out of scope, the byref I returned is now out of scope as well and can no longer be used.
I see. So this is the lifetime of the struct implementing the interface.
Yeah.
Yeah. Okay. Okay. Thank you. Because I was wondering, like, in what sense is that more conservative? But that
Yeah.
explains that.
You can't have a function that returns a span that it got from an input parameter because it now doesn't know what happened to the input parameter.
Got it.
All right. I assume there's no contention on that. Okay. So where do you want to start?
Okay. So for this next set, uh, these cover APIs that we've already reviewed and approved for tensor primitives. Tensor primitives being the one that operates over raw span buffers that don't contain any information about dimensionality, that don't support more than 2 billion elements, etc. So this is bringing the primitive, more unsafe concept and bubbling it up to the type safe and the type safe concept where we actually have a multidimensional piece of data that tracks the strides, the overall shape of the underlying data, etc. And so this entire next block is basically just a mirror of that surface area where uh, inputs that are not mutated come in the form of read-only tensor span. We have the overload parity for where you have, for example, the cosine similarity. There's two overloads there, one that takes in two tensor spans and one that takes in a tensor span and a scalar so that users can have that implicit broadcast support, the same as we have in tensor primitives. Then you have the API overloads that return tensor of t, meaning they allocate a new buffer. And you have the ones that take in a tensor span as the destination in the same general format as we have for tensor primitives. Now, the things that I imagine you're going to ask about are, one, why in? And two, why the biref return for the one that takes the destination buffer? So the reason that they take in is because read-only tensor span and tensor span, in order to be allocation free, are large structs. So they are the specialized scenario where they actually are effectively a 112 byte struct. That is the only way that you can have a multidimensional span that is also allocation free. They are read-only struct, so there's no concerns about implicit copies happening. And the in just makes it so that users can continue accessing the API without having to consider the fact that it's a large struct. They just continue passing in the tensor span as they normally would, and everything just works. As for the biref return, that is a question about composability. And I know that one's probably going to warrant some discussion from API review, and there's going to be people on both sides of the argument. I don't have a base reference myself, but there's other people that have been working on the tensor primitives and that have been using the prototype that did feel very strongly about this. So it basically comes down to that the ref read-only return is always going to return destination. And it simply allows you to use the one that takes an explicit destination buffer in the same way you would use the one that implicitly allocates. So that way you can chain the operations together, you can nest them without creating a million different locals and temporaries, and everything just works.
Where does the thing that it's returning live that it's returning at ref?
It's got the same lifetime as destination, so it's literally returning. So destination is in tensor span destination, so it's already a biref. We are just returning that biref, the unmutated biref that was passed in.
So cosine similarity returns destination? Oh.
Yes.
Okay. So you're saying it writes to destination and then you're returning it.
So that it can be composed.
Oh, so when you're saying composability, what you really mean is fluency.
Sure.
Which we say we don't do.
ASP.NET Core does love you. No, it's nice. What are we looking at actually? So for the cosine similarity with and without the ref read-only returns, those alternative designs?
No, those are the same design. The first one is one that doesn't take a destination buffer. It allocates a new tensor and returns that.
Oh,
the latter overload, the second two overloads there, they take in a destination buffer. That way users can have an allocation-free experience. But they have to manage they have to explicitly specify what the destination is going to be, make sure it's the appropriate size, etc. The fluency here is so that you have the same overall experience between both the one that allocates and the one that's allocation free. Otherwise, you have to explicitly break apart the uh, the APIs and create a much more complex and harder to read algorithm.
Yeah, yeah. So just taking the position of we don't generally do fluency.
Right.
I can see where it gets weird that if you say, I want the cosine similarity of the cosine similarity of two things, that works until you then say, oh, I have two stack alloc scratch spaces, and then it says, well, now instead of doing function composition, you have to go rewrite things. So it's not so much that you can do something dot something dot something, it's that you can pass it in as the argument of another function. So,
Right.
so I think it's
Do
a
you have
little
some-
And that's
weird. It
kinda-
makes sense.
Yeah,
Do you have
that's
some
kind of why I
sample
went
code
with the
that
word
shows kind of like
composability.
general usage of tensors? You don't, right?
No, it's kind of the same as you would write for normal math. You could replace all of these tensor span with just t and consider it like float, for example, and it basically works the same way. Where cosine similarity that takes in two spans and returns a tensor, you're really just taking in the input value you're operating on. So float, and then you're returning a float. The nuance with the second set of overloads is you have many floats, and so you need an actual buffer to contain all of them.
Yeah.
You want to be able to support the user providing the buffer so that you don't force allocations. That implies taking a destination buffer. Normally, we have that return void whenever we take a destination buffer. But then you can't do, for example, you could no longer write mul x add yz destination. You would instead have to write mul x, you would have to write mul xy destination and then add destination z destination. So it breaks you have to explicitly break it into two functions if you're void returning, and that
true.
greatly hurts the ability.
Well, I wouldn't stress the greatly part. I think it depends on your frame of reference. I look at what you just said, and I then think, wait, where is this writing to? Like, I have to logically think through and go look at the definition to know that it's returning the destination again, and that it's not, creating some new space that it's returning, or like you have to kind of really understand the shape of the thing you're talking about to understand that what the call site is doing, which is why I actually prefer the non-fluent version, because it's very clear in the shape of the thing that I'm calling. This is the input, this is the output, this is the input, this is the output. So I still prefer the non-fluent one. I'm not going to jump up and down and say no way, but I think there are pros and cons to each, and saying that one is great, in some ways greatly simplified than the other, I don't think that's true. I think it's in the eye of the beholder.
I think
depends.
for that. Go ahead.
Okay, like all I was gonna say is like it is kind of straddling the line between like a fluent API and just like mathematical operators, right? Like the input and the output domain aren't exactly the same, but if you think of it like, cosine on scalars, or just like, I don't know, or just like the overloads that allocate, right? Like making it more similar to that doesn't seem super bad.
Except the ones
The
that
other
allocate,
thing
like you're returning a new thing. Like the ones that operate on Tensor, you're getting back a new object. You're not getting back state that you happen to provide to the first call.
Is it
Yeah.
the state, or is it just the output buffer?
But the same thing. That's what I meant.
Yeah.
The output, yeah.
It's scratch based, but like it's not reading
It's
right?
not scratch space. It's where your result ends up.
Okay, scratch space is the wrong word. You're right. Sorry, but the point is like it's not reading it.
It is reading
Like
it. When you pass the output as input to the next thing is reading it.
Yeah.
Okay, sure, but I guess it's the space you're putting the return value of the other method. Like I kind of see making it void, right? Like that's the alternative, right? And then just write another statement that then uses the in argument again, the destination.
I mean, this is also a place where if we say we're doing the void because it reduces some head scratching, somebody who wants to write the ref return wrapper can do so.
Sure.
You can write an extension method that says take the arguments and then return destination.
You could write a void wrapper too. It's like, which one do we prefer?
Well, so I think there's two considerations there. One of which is that you can't really write an extension method. You have to write a helper method because overload resolution will always pick the existing one.
No, this was static
anyway. The other consideration is just that if we expose void returning, users have to go and write a helper method if they want to, if they want the composability. However, if we have the one that returns the buffer instead, there's two benefits. One, people who want to use the composability can, but people who don't want to use the composability can literally not use the result. They can write this exact same code they already were. But also, we can more trivially allow users to get the sliced buffer, meaning the destination, since destination buffers can always be larger than appropriate, we can ensure that it is sliced to the exact length. That way users can use pooling and get the correct sized output for passing into the next input trivially. Otherwise, they have to do extra computation to determine how much data per dimension was written, and that's going to make that means we're going to also need to take in a read-only span init by elements written per dimension type parameter.
Wait, I didn't understand that part. You're saying the ref return wouldn't be to the destination; it would be to a sliced destination.
Not the exact destination, it's a sliced destination. Sliced down to the exact amount written.
But what? I don't understand that. Because then your ref isn't pointing to the exact in argument anymore. It would be pointing to a new span.
Which I don't think the ref rules would say that was allowable.
You're right. It would need to be a non-ref read-only span. It would need to be a regular span in that case.
Yeah.
Wait, does that mean you need a length for this or something if you weren't returning the ref?
Right.
Tensor span?
If we're not returning, then we need some kind of way to pass in how much was written per dimension, which means that we need it's not just an out int bytes written, it's an out read-only span elements written per dimension, because you need one for each dimension that exists in the
No, you
can't.
Span. You can't out a span without allocating it. You could take in a span of dimensionality and then
span input buffer,
and then another smaller span of what's the number of dimensions that it wrote to the number of dimensions, or to the lengths thing. Ad infinitum until you get down to an int. But
yeah, it's not a nice experience.
Right. So I wanted to make sure I understood what you're talking about. I think what you just said is that the APIs on the screen are actually not what they would be. That either all the methods would be void returning and take an additional out something to describe the lengths, or it would not be what's on the screen, and it would, instead of taking returning a ref read only tensor span, it would return a tensor span.
Yes.
But I think what he's saying is that it's only some APIs, right? Or is it all APIs?
It'd be all of the APIs that have the destination buffer.
I see.
I mean, if I had to choose between, if it's no longer the case of we're doing it for fluency, but we're doing either we have to return some new information and we have to return that as either a return value instead of void or an out parameter, I would certainly choose the return value. And if fluency then results, great.
Yeah. I mean, my concern is like if you just look at what's on the screen right now, right? The first line of answer where we don't pass in the temp, they all allocate, right? And now you're like, oh, I'm concerned about my allocations. Now you inject the temp thing in order to avoid those extra allocations. Well, it seems like, well, I can easily miss a comma temp in some of the APIs. I mean, some will have them, some won't have them. And it won't be obvious to me where that is, right? Versus if we say they're all void returning, well, you can't really mess it up at that point because it's like, well, if they allocate, they have a return value. If they don't allocate, they have an out.
Yeah.
So I guess it also depends on how important is it for you to reason about like, oh, am I actually always passing in a destination when I'm supposed to, or am I accidentally allocating somewhere that I'm not aware of?
I think it's
I'm
actually
confused,
worse
though,
because I
code-
think this is now unsafe.
But is the code in what Jeremy's typing, is that actually valid? There are overloads here that deal with tensor. I didn't think those took a destination, and there are ones that deal with tensor span that do take a destination.
Oh, I think they're all supposed
let's
to have been
see.
tensor span. Yeah, cosine similarity. Oh, I see. Cosine similarity is tensor spans in and tensor out.
Well, presumably I can pass in a tensor as a tensor span, right?
All right.
Right.
Okay, I was gonna say the fact that these aren't the same return type makes me move to it should just be void. But if there's a one-way conversion,
If it was a question of ref return tensor span versus void and no other change to the signature, I prefer the void. But if it's a question of ref return read only span actually doesn't work, and it either needs to be void and with an out or tensor span return and no out, I would choose the tensor span any day of the week.
yeah. But this also can't be right because you couldn't have returned a tensor span that was a read-only tensor span.
No, this wouldn't be a ref.
Yeah,
I'm saying you delete the ref read only.
Okay, so you delete the ref and the read only. Okay, I was wondering.
Because what Tanner was
So just
saying is
public static tensor span.
this needs to return a sliced span, and it can't be a ref read only in that case because we'd have nowhere to allocate that we could pass a ref to.
Yeah, and we're not changing.
Oh, but
the
destination's
destination.
obviously not read-only because you're writing to it. Okay, never mind. I was like, this is read-only. Read-only became writable. Like that doesn't make sense, but it's the destination.
And the destination isn't a ref,
Right.
and we wouldn't want to make it so.
Because so with this shape, right? You get the like, oh, I just need to throw some temp space at it. If this is now returning temp, then I think it becomes not at all obvious that this is now using the same thing as an input and an output parameter, which means it's probably undefined behavior.
Well, it's still executed in that order, right? So you still have the ordering guarantee.
Yes, but this says return temp, which means this next line is cosine similarity of temp, c, temp, which means that
If it's a ref return, which it's not, right? But like in that world is what you're talking about.
right. So I guess in the way that it was proposed, because then it would have said it's both the in and the destination, and then
That's
you get the great like
for all APIs.
what order does it do things in? Does it have a sensible I will give you the same answer as you would expect, or does it not? So I think that would
it does things in the C# order.
But we don't have a C# order for like multiply that is I'm writing to your destination. I mean,
there's absolutely a well-defined C# order for line 30.
Okay.
Yeah, and tensor primitives, we explicitly said that having having an input and the destination buffer be the same was okay. It's just that having them overlap and not be exactly the same is incorrect.
Okay.
So provided they start from the same point, they're safe.
So the functions have not overlaps protection, but identity protection of an input and an output. It will give the right answer as if this said temp2, it will be correct. So okay.
Interesting.
All right, so I think looking at the first one, we're assuming iRoot functions is correct. I think we're happy with the returning one. And then the question is, what are we doing with the destination writing ones?
Do you have like a
It sounds like
a rule of thumb? Like, how do people know which APIs would allocate and which ones wouldn't?
the one that returns tensor allocates, the one that takes in a destination does not allocate.
So everything that doesn't take a buffer by definition allocates.
Well,
never
and
have-
returns class.
Unless it returns like a scalar, right? That's
Is that entirely a true statement, Tanner? If we return a sliced tensor span, and it has more than whatever number of dimensions have built-in space, won't that still allocate?
Yeah, but users are in a super esoteric scenario there where they're using more than like 5 dimensions, and we basically said that's non-standard and outside the scope. Technically, if T is a class, that would also allocate. So from the perspective of the thing we're returning itself is an allocation or not. Like, do we reuse what the user's already defined?
I see.
So string theorists will allocate always.
Right.
All right.
I didn't realize over 5 dimensions was supposed to be like super esoteric for this API. I know that's like esoteric for physics, kind of, unless you're a string theorist.
Okay, that's kind of like I'm surprised that it's 5. Like, why 5? Well, what is the magic number 5?
Because so 5 is what we know that 0 dimensions, so scalars 1, 2, and 3 are all very common.
Yep.
4 dimensions is then used for some types of audio processing, and 5 dimensions is sometimes hit for other types of more domain specific machine learning. Once you hit 6 dimensions, you start getting into the realm of like, yes, people can do it, but it becomes so rare that it's not worth making the underlying struct bigger to handle it. We wanted to find a reasonable cutoff for what's inline versus what needs to force allocating a buffer to track the extra metadata.
Gotcha. Yeah, I always thought of tensors
And we can
as
freely change
n-dimensional
that
where-
in the future.
where n is arbitrary, but it sounds like it's not as arbitrary as I thought it would be, so it would make sense to optimize for those.
I mean, I assume it's like big integer, where I have some guaranteed allocated space that I can store answers, and once you need bigger than this, I have to allocate an array. And now, anytime you make me do work, I have to allocate another array.
Yeah. And then my other question was kind of
And
related.
since these
like,
are all taken by in,
yeah, go ahead, finish that thought.
okay, since they're all taken by in, it means that we are free to change the underlying we can change how many inline dimensions are tracked inline in the future without it being a breaking change based on user data. So if we end up finding out that, hey, 6 dimensions is actually really common, or becoming really common because ML has evolved, because they're taken by in, we can change the struct to be larger, have more inline data, and it won't break.
We can change it without that too. The runtime handles struct resizing.
Yes, but if it weren't taken by in, that would potentially become a perf de-optimization, because you would potentially grow past a particular size where it's no longer efficient for the CPU to do the bival copying.
Fair enough. So okay, right. The APIs would all continue to work. The program would be functionally correct, but the way that it has to pass the values might change. Sure.
Yeah. I mean, in practice, what you just said, Tanner, also depends on how the user writes their code, right? I mean, nothing prevents them from writing methods that take read-only tensor of span without writing in, right? So they can still hang themselves all day long, right?
Yeah, but we will probably end up having some kind of analyzer to help tell people you want to pass this by in.
Yeah. I mean, kind of on that vein, like, I know when we talked about span in the very early days, there was some concern about tearing, which I think we gave up on, right? Because we store a pointer-sized field and an int field. Presumably the same applies here, right? Because they're bigger than they're what is 128 bytes or whatever. You can't have multi-threading read those things safely when they're written to, right?
If you had a by value tensor span local, like tensor span x, and then you said x equals y, that has the potential to tear. But that's also stack local, and the runtime in general says that stack locals are not presumed to be cross-thread visible and is allowed to make optimizations assuming that they're single-threaded. So the tearing's not really a concern.
And then for fields, it's not, because they're by definition refs.
Yeah, the individual fields are primitives, and each individual field is going to be atomically needed.
Yeah. So we're kind of off in the weeds. What is it that we're actually deciding between now? Can we write out the 2 signatures that we're actually debating between?
Yeah, because I don't actually know what they are. So.
Yeah, so this or it'd be void, and then I think span init elements written. Those should be the 2 signatures. The second one could potentially be also could be out int lengths written. Yeah, I think the last one is the one that allows you to pass in a too large elements written buffer as well. The second one would require elements written to be exactly the size as the destination rank length.
Which,
holy shit,
if any of these change rank, would be a thing that you would have had to have known ahead of time.
Yes, so there's complexities there that are complex. And the name is terrible. That was just like a throw together name.
If we actually go with the void returning one, then the very next line ought to be something like destination dot slice with the things that are being passed that are returned in elements written and lengths written, right?
Yes.
Yeah, that's going to be a
pain in the butt.
Yeah, so that'd be cosine similarity of
I mean, you could out the tensor span, but
Just
at
gonna
that
call it
point,
cos.
like, why aren't you returning it, right?
Would become cos of A and B to temp and ranks and out and ranks written.
You said it wouldn't be a single int, though, right, Tanner?
No, so the ranks written would be would the final, so the difference between the second and the final one there is the second one just takes the elements written per dimension, and it would require that that span be exactly the same as the destination length throwing if it didn't. And the latter one is basically saying the elements written buffer can also be too big, and I'm going to tell you how many ranks were written to the elements written buffer. It's because you've got two levels of dimensionality that you have to reduce down to the scalar instead of the one level of dimensionality down to the scalar.
Right. So I think
Right.
A, B, temp, and ranks, and then out ranks written. A, B, temp, ranks, out ranks written. And then you slice the ranks to the number of ranks that were written to pass to the buffer to slice to be your actual shaped temporary input, and then you call that one. Yeah, I think I got it right.
Okay, so it's like
Yes.
2 additional outs, one
Which is
span, the other.
altogether a not great experience.
Right, like at that point you'd like would out the tensor span that you'd out temp2 instead, right? But at that point, like, why not return temp2, which is the original proposal?
Yeah, I would agree with that. Are there any other downsides? Like, is there any power scenario where you would want these outs, or is the return value sufficient?
The return value should be sufficient because we're slicing it. We're doing that slicing for you, so that way you don't have to have it. And a user who didn't want it sliced could just consume the output they passed in directly. So all the information's still there. It's just in one nice little type rather than split up into multiple outs and requiring the user to do multiple operations.
Yeah.
Yeah, at that point, I think the lesser evil is the comma temps.
The lesser evil is the what?
Like just having a comma temp in your inline expression, right? From the verb, like line 22, if all you have to do to use stack provided stack, you just say a comma b comma temp comma c comma temp, right? And it's like, well, if you forgot one, we allocate, but at least you don't have to do, in it, because I mean, if you look at line 24 to 26, I don't think the problem is that code. It's more like if you actually do something interesting, you have these lines repeated 4 or 5 times, which now means you have several ranks. You have several ranks written variables. It's going to be very error prone to use the correct ones. And at some point you copy paste, use the wrong one, and then all your tensors are fucked up because you sliced the wrong thing, right? And then it's, worst case is that might work in many cases because, well, the rank happens to be the same across those calls. Sometimes it's not. And so it does seem to me that 24 to 26 is just not only very ugly, it's also very error prone in any sort of real programming. Versus the worst case that can happen with the original design is you forgot to pass in a comma temp, so we allocate, but at least you get correct results. And like the allocation thing, well, you can measure it, you run a profile, and it's going to tell you what you're doing. And if we really wanted to, we could have an analyzer that detects that, oh, you passed a temp space in some of the calls, but not all of them. So that's probably not what you intended, right?
I mean, if we really wanted to, we could just not approve the allocating APIs. But I think for some scenarios, we assume people don't want to bother.
I mean, that's fair, actually, that would solve that problem too. But I suspect that's not going to be convenient for
so
people that just try to learn.
Right. There's things like notebook scenarios where this is going to end up getting used where spans don't really work outside of being passed into a method because they can't persist across two interactive statement executions, which is something that things like interactive notebooks need to do better about handling in some context so that you can still make some stuff work. But in general, you really need the allocating versions for convenience, for learning, and even for places where you don't want to or don't need to manage the buffer. Like the final statement of a chain of calls might decide to allocate a new buffer, but the rest of them use temporaries, a shared temporary.
Yep. Right. So, yeah, I guess if we wanted to rewrite this to do full temp, then this would look like that, and then you'd do that again.
Yep.
Where you get to reuse the same slice state. So you don't make 100 ranks written. You would just presumably you would use the same one over and over again, but this does look
the thing
much
is,
nicer.
Yeah, I mean, I think 33, I know what's going on, and 24 to 27, that takes me a moment to. I mean, at that point, you would write a comment that is basically 32, right?
I mean, people would create a helper that returns.
Right.
And then they would write this code.
Yeah, I don't know. I mean, I've seen code that uses vector of t for SIMD stuff, and it's not pretty when you have a lot of local variables and you have to reconstruct in your head who's passed to whom.
Because what's interesting is it feels like calling it destination is the wrong answer. Right? It's really
Well, you could call it.
it's really scratch space. It happens to be the return, but since we have to return it by value, it's actually not the return.
I mean, that's the thing. Like, Steven seemed to be very opposed to that, but like, why couldn't we treat it as scratch space? Because it is, right? It's read from, it's read from, but ultimately, so it's written to and it's read from, but like it seems to be more like an implementation detail. Like, you don't have to know that.
My concern with calling it scratch space is usually like, use this, and when you're done with your operation, I'm free to reuse it for something else because it was scratch, right? It was a temporary thing. But the return here wraps the scratch.
Gotcha. So if you mess with the scratch space, then you destroy the return value.
Yeah, I guess because the difference is the tensor span itself. So I guess it's writing to the same underlying memory. Yeah, which I guess is really what you're passing in. You're telling it where it's allowed to do the writing. The answer is using that same shape of memory, but all right. So yeah, it's not about the span itself; it's about where it's pointing.
So it is destination then, right? Are you okay with that?
Yeah, it's a weird destination that you really shouldn't talk about it once you've passed it in.
Because the correct shape is the output.
Right, because you don't know what shape it wrote to the destination. It tells you that by returning the output. If you linearized the span, all of your answer would be in it, but you don't know.
I mean, if you feel better, you could call it buffer, because it kind of implies it's just space, but it's space you are not free to reuse afterwards.
It's not just going to be in there. It's going to be at the start, at the same starting point, and it's conceptually then no different from any of our other APIs that take a span destination and an out int bytes written. The destination there is not the actual destination span. It is a buffer that points to the same starting destination, and because we don't return it, you have to slice it to get the actual destination.
I guess that's fair.
Yeah. I
Yeah,
guess
I
the
can
part
agree
that's
too.
weird is like whatever expression you pass in here, which is one presumes would be a local, but whatever expression you pass in here, you don't really use again after that point because you're gonna use the return. Like so
Yeah,
it
I mean,
that's where it's just like the shape. Like calling it destination is probably the best answer. It just feels a little. It's a little off of our normal span writing pattern because unfortunately this is what would be the correct thing for our span writing pattern, and this is just nonsense in context.
Yeah, I think that's how I would see it. It's like it is logically the same thing. It's just ABI wise encoded differently to not make it a pain in the butt to use.
Right. Because it'd be the same as if all of our things that are span writing out elements written and are void, and we said, oh, it'll just return destination.slice of the thing. It's like,
Yeah.
I will say,
Eh?
like, similar to where you were earlier, Jeremy, like with this line 32, right? So you're passing in the destination temp to the inner cosine call. It's returning some projection of temp, right? Which is then a parameter to the outer call to cosine, but then again, you're reusing that same destination when it's a parameter. Like, I know we talked about how this is like a well-defined order and therefore safe, but as a programmer, I'd be like, is it?
Yeah.
Because like it's both the input and the destination, right? For that outer call of cosine.
yeah. Is there ever a case where the composability of this would not be fair, Tanner? Like, take any function here. Like, if the answer is they have to have the same or element 0, it would be if any function ever returned. I took in a 5x5 and returned the 3x3 that's in the middle of it. Then now the input would not be the same 0 aligned as the destination.
None of them should be that way. The APIs that change that do like that is all of the APIs. The point 0 of the destination is going to be the starting point of the resulting tensor that's being produced by the operation, and they're all taking into account that if an input and the destination overlap, that we're not trashing data before it's been read, so that we don't pollute the operation. So they're all sensible and correct here.
Okay.
Yeah, I guess it's just something you got to get used to. It's like it's safe for these APIs.
Yeah, I'm just making sure we're not footnoting here. So.
Yeah, no, me too. But if that works, it's nice. Like it's convenient to just kind of not have to think about it. Like it will do the right thing. I use the same memory for input and output.
Yeah, so presumably tensor span has a dot to tensor, right? Like there's a way to get from the So
yes,
I wonder. So going back to the do we need both shapes? I wonder if we always want the shape where you have to get past the destination, and in notebooks they just have to end with dot to tensor.
that would require you to pass in a destination buffer, though.
Yeah. Anytime you wanted to use this, you'd always have to have a local that you pass as the worker space, and then you return dot to tensor of every stuff. If we think that that's bad usability, it's fine. Just we're gonna have twice as many overloads, and if the answer is all intermediate calculations should be using the one where you write to the destination, it's like maybe we don't care to have the polish of the final one being simpler. We just say you get to write the one line that says I'm done now. I'm just asking.
Yeah, I can see the case for that. It's yeah, I think the usability there is significantly bad for users who are trying to just learn and get started in this space. Especially if they're just like it's very typical for data scientists to basically try and write the smallest amount of code possible, just play around with results and see what the outputs are in an interactive environment. And if they have to know, well, now I've got to tensor at the end of every single one just to make notebooks work. I imagine that we're going to get very quick feedback of we need the other overloads anyways.
Fair enough. All right, so I think that means we like this shape. We return tensor span, which will be a slice of destination. And that's the way that we convey the
So it's
the
just
ranks
dropping
and the rank ranks.
Yeah, so it's just going to be changing from static ref read only to static. And that should be a global find replace that can be done.
Okay. And I assume we didn't do the reflexive scalar first on cosine primitives, because you have vector vector and vector
Right.
scalar, and I assume we didn't also add scalar vector. So, okay.
Right. We've got scalar vector in the places where it makes sense because the order matters. And we didn't in the cases where the order does not matter.
Okay.
So add, for example, has just scalar as the second. Divide has both scalar as first and scalar as second.
Amusingly, it looks like distance is reflexive.
Right, because distance, because if x is larger than y, it will be positive. Otherwise, it will be negative.
Gotcha.
So now that we've figured out the convention here, the rest of these should be pretty straightforward to get through. Where, like I said, for this first list, we're mirroring what's in tensor primitives, but operating over tensor of span. We've got overloads for the ones that return a tensor. We've got the overloads that return a tensor and that take the destination buffer. The signatures then have the scalar parameter where it makes sense if the operation's associative, if the operation is commutative, then we only have the scalar in one position. Otherwise, we have the scalar available in either position. And so the first set here is a mirror of what we've already approved for tensor primitives. So cosine similarity, distance, dot, norm, product, sigmoid, softmax, sum, the basic, all the generic math operations, and I've got them sorted by the corresponding interface they exist on. So add, the bitwise operations, leading zero count and pop count, and they are all constrained to the minimal set of interfaces, just like we opted for with tensor primitives. Now, with comparison operators, there's a discussion point here. With the comparison operators, this is following the same convention that we opted for with with the vector types. So on the vector types, we currently have a set of 3 APIs that exist for every relational operator. There's the regular operator named, for example, greater than, which returns an array of masks effectively. In the case of tensor, it's a set of bools, indicating the per element equality. And then there's 2 variants of that exist called relational operator all and any, where those correspond explicitly to do all of the values are all of the values in X greater than all of the greater than every corresponding element in Y, and then any are any of the elements in X greater than the corresponding one in Y. And so there's the set of 3 there, and it's following the same convention that we have for the vector types. So it's the existing convention there, but because we've not done that outside the vector types, I wanted to make sure it is explicitly surfaced here, and make sure that we don't have issues or concerns with that coming here as well.
So for the vector types, it looks like we never mix vector and scalar on the any.
Yes, and so for the vector types, the reason for that is because we know that the vectors are hardware primitives when they're accelerated, and so the natural API of just doing create scalar, which will broadcast it up, is a free operation, and the JIT is able to recognize where it's relevant. For tensor, these could be arbitrary length, where you could potentially be broadcasting gigabytes of data, not just like 16 bytes. And there's no way for the JIT to go in and optimize and recognize and handle that without making all kinds of changes that would never get through PR, since it would require complex JIT and moving this down into corelib. And so for tensor, we actually do need to be explicit about taking a scalar value so that users can avoid the costs there.
Yeah, because what's weird is in my brain, the greater than any makes sense here, but on this one it needs to be any greater than. And I know we're not going to break a method group for that. So I'm just trying to think does it feel natural or does it feel wrong? Or sorry, does it feel natural enough? And the answer is probably yes. Again, the all, so really it's the ones with the scalar on the right with the any and all that just feel unnatural to me, but they're probably fine enough. Nobody else is complaining.
Mm-hmm.
And oh, right, this one is element wise, so it's returning the elements, and these are reductions down to a single bool, right?
Yes. Yeah. In a more ideal world, we could just have like an any and all function that operated on a tensor span of bool input, and we wouldn't need these overloads. but we aren't in a world where we have a way to create zero cost lambdas so that this can actually be efficient and avoid the allocation and avoid the walking large amounts of memory twice. It's an unfortunate scenario for these types, but
So
that's kind of the world we are in today.
in the talk yesterday of how search values is implemented, they talked about how they have some generic static funcs basically that they use for generic composition to do optional negation, etc. Would this be better if we took a no, because we'd have to specify it as a generic parameter. If we moved any and all to some sort of function, and then you pass the any and all func. But
right. The yeah, the consideration there is we can do something. It would affect it. What it would look like is effectively a public static bool, any t, and then basically a t operator. And then T operator would be constrained to an interface, something like where T is I action, for example, or in this case, I func of T bool. And basically, instead of taking a delegate predicate, you'd take a generic that's constrained to an interface that looks like a delegate, so it's got a invoke method on it, and that actually is incredibly optimized by the JIT. It plays into generic specialization, it plays into inlining. It is infinitely better than delegates in every way except for you can't use lambdas with them, and it requires users to manually write out a struct type that contains the invoke method that contains the code. There's a proposal for the language to actually make that first class and allow lambdas to bind against them, but that's not going to happen this release or possibly even next release.
Right, but if it was taking static functions, then this would have to become greater than of t comma t resolver, and then you would have to call it with greater than of int comma resolver dot any, and then you'd be like, oh, that's ugly.
Rather you'd invert it so that you just have greater than that returns the tensor of bool, and then you'd have a all function that takes in the operator, so you can pass in the greater than comparison instead. So you're basically saying I have an all reduction across all results computed across, rather than saying I've got a greater than operation that returns different results depending. It kind of like how LINQ already does its all function.
Right. Does I mean, you could do that already with a extension method on tensor span of bool called any and one called all that did that, but you then have to evaluate the full tensor span, and because presumably these can short circuit.
Right. Those ones
and
short circuit
can't.
And don't require full evaluation, and that's why we've got both overloads today.
Right. So I'm just the part where you'd have to the part where you're now passing in the greater than to something else means it would have to full evaluate, unless we do all sorts of sneaky, like, yeah, I don't know how we would even sneak that in. You'd have to inline the full function into the caller.
Yeah, the way we implement this internally is we basically have a bunch of interfaces, I unary operation, I binary operation, and we have some helpers called invoke span into span and invoke span into span and such, and they take basically the functional interface as part of a constrained generic. And so we just have we've got a greater than operator, a greater than all operator, and the difference between them is one just calls vector 128 dot greater than, and the other one calls vector 128 greater than all, which is basically greater than does not equal, or greater than equals all but set. And so it's incredibly simple and allows huge amounts of code sharing. It's just not a nice experience for the user to consume directly for the typical case. And that might change in a couple releases.
Yep.
But not in the near term.
All right. So, Emo, Stefan, do either of you have issues with the 9 functions?
I don't think so. Just so you're saying delegates don't get inline properly, so that's why we don't have like functional overloads for all of these. And I assume you like considered adding like a second generic parameter that could be a custom eye comparison operator, and that would be gross. Or is there another reason that would be a bad idea?
Right. For the purposes for these purposes where we're explicitly doing a greater than and stuff, we want it to do the operation. If we were to have a different one that took in eye comparison, we'd probably call it compare to, and it would explicitly take eye comparison, just like the other APIs throughout .NET that do that. So they're kind of different considerations. One is operator, and the other is eye comparable. And those do differ in many cases, like float and double.
Yeah.
Right. And like the other APIs, right, aren't relying on eye comparison operators. They're relying on like the runtime interface, right? So you lose some, or not runtime, sorry, the non-static interface. But the point being that it wouldn't inline as well, right? Is that what you're saying?
Yep.
And it's not actually 9; it's actually 12 because I forgot that So that is greater than is 12 functions.
Yeah. I mean, it's very similar to vector of t in the sense that if you want the stuff to be fast, you just can't do things like we do it with primitives. I think that's fine. It is the domain you buy into.
Yep.
I mean, some of these are, yeah, I guess it makes sense. It's like you could, yeah. So is it 12 things for every kind of comparison, greater than, less than?
Well, and then plus 6 more for the equals.
Yep. Greater than or equal, less than or equal. Yep.
Oh, sorry. It's actually another 12
we don't
for the
have
equal.
not equals, notably.
So 12 greater thans, 12 greater than or equals, 12 less thans, and 12 less than or equals. Well, good things to
I mean, in
drops.
fairness, it's really
He'd cry at
Yeah,
the
and then there's
function table exports.
it's really 4 per operation, right? Because and then the other ones are just overloads based on the types you're taking. So
It's 3 method groups per.
yeah, sorry, that's what I mean. Yeah.
Yeah, because you get the vector, scalar, vector.
Yep.
And then that with I accepted temporary destination. And then the alls and any's. And then double it again for or equal.
I mean,
Yeah,
there
my
aren't
point
any
is that
that
it's not that much of a concept count because it's
Right.
it's just logical operations and they're like logically grouped.
Yep. Yeah, like my only one is the any's. The language in my head says the middle one, the any should be on the left, but that would be a terrible, terrible thing, and I'm not advocating for it. So my brain will get over it.
Stefan, you were trying to say something as well?
No, I'm just all I was saying is I'm fine with the number of overloads. I realize it's a lot, but like there aren't any that are obviously extraneous. Like they kind of just complete. To your point, like you're gonna have to accept the operators in one order, why not the other?
Right. And while this is giant and fills the screen, again, it's we have to talk about what's the explosion for greater than, and then to the GitHub character limit, it could have been repeat greater than or equal, less than or equal, and we'd be like, oh, okay. And so then the whole proposal would actually fit on one screen. But
Yep.
so it's not. Yeah, the concept count is low. The number of functions that get added is high, but if you are using the shared runtime, you don't care, and if you're using a standalone app, then the trimmer will delete the 100,000 of these that you don't call. So
Right. This isn't a NuGet package, right? Like I assume, and not the shared runtime. That's why you don't care, or is it not? And we don't care because it's just already big.
this is Is this going to be part of the shared runtime?
Out of band NuGet right now.
So you're full OOB because we don't have internal consumption.
It may eventually be part of the shared runtime, but
yeah, and then you get to join the rest of us with
out of band package
with terrible half in,
and
half out.
hopefully it stays out of package.
Yeah. Okay. Yeah. So yeah, there's trimming. It's out of band.
Yeah.
It seems good.
It wouldn't be a Tensor API if it wouldn't come with 5,000 APIs.
Yeah. Interestingly, I think the fact that it's OOB means we should care more about the method explosion here, because every individual application that uses it's going to have an independent copy of the same bulk, but at the end of the day, they're probably not all that big. And
that's why you AOT and trim. I don't know.
Well,
maybe.
the implementation for all of these it actually boils down to a very small amount of code, because we're utilizing tricks like static abstracts and interfaces and generic specialization to ensure that all of them go down to the same core function.
Right, and these two, I presume they're actually going to be implemented as not the greater than version. So this is not greater than all, unless you're saying you actually have to call the less than because of double being stupid. Yes, Nana's stupid.
Yeah, we take advantage of utilizing the inverse comparison where that's possible.
Yeah. So while there's a lot of every individual one, if you were to write out what does this function do, you'd say, oh, this is a whole lot of code, but really you're going to, in addition to the concept count not being as much as it looks on the screen, it's the implementation is they're all going to have most of this is 2 core functions. So is my guess.
Yeah.
All right. Division. Are X and Y what we called them in tensor primitives?
Yep.
All right.
Yep, we went with the name of X and Y for almost everything because there was too many where they didn't have well-defined names and where we had used X or F or D in other APIs. And we had discussed whether we wanted to name some of them left and right or some of them more sensible names. And we had eventually decided on everything, just X, Y, and Z, except for cases like fused multiply add, where we explicitly named the third parameter addend.
Okay.
And the equals does not have the full 12. It only has 8 because they are commutative. So we don't need to take y on either side. We only need to take the scalar on the latter side.
And
then we've got the exponentials, the floating point functions for ceiling, floor, reciprocal.
Comparison operators is the correct constraint there?
No, I think those ones should be I-equality operators. That would be a copy-paste error on my part.
Yep. notes. Okay.
Yeah. The exponentials, the floating points, including reciprocal, truncate, rounding functions, the IEEE floating point ones, which includes the ones that aren't part of the core, like trigonomic functions, like A tan2, fuse, multiply, add, IEEE remainder, ilog, linear interpolation. LARP is an interesting one because it is a three-parameter case where uh, none of the parameters are commutative. And so the rather than being three overloads like most cases, or four like in the case of fuse multiply add, it has I think seven, because you need the combination of each individual can be scalar or two can be scalar to avoid the allocation and memory walking overhead.
I was gonna say it was 8, but 000 is not valid in context. So scalar,
Right.
scalar. So it's all
Yeah,
8 minus scalar, scalar, scalar.
Don't need the TTT.
Yeah.
Right.
And then double it for temporary destination. And
We then have the hyperbolic functions, the logarithmic functions, multiply, the standard iNumber functions, including copy sign and the index of, and then the various max and max number functions. The number base, which includes absolute, the conversion, the max magnitude, since comparing magnitudes is valid for all number types, including complex. And then multiply, add estimate, which I noticed I put the wrong interface constraint on. That's iNumber, not iFloating point. That we had originally, when multiply add estimate was originally proposed, it was on iFloating point, but then we changed it to iNumber because it was applicable to all types, and we wanted it to be available for people who didn't constrain specifically to iFloating point. So that was just a point in time. I forgot to fix it. The power functions, the shift, or the root functions, almost missed that one. The root function is a case where it's worth calling out that much like on tensor primitives, we require the n to be consistent for all. We don't allow you to specify a different root per, because there's no way to optimize a different route per, and we don't want to point people down a pit of failure there. So root n is a case where we require the n to be consistent for all tensors you're operating on. Then we've got the shift, subtract,
where
the
shift,
trigonometric,
similarly,
and then
you're
the
not
negate operator for linear negation.
similarly you're not allowing a per element variance in the shift.
Yeah, so yeah, we actually could allow per element variance, but that's not something we've got on tensor primitives today. It's a little bit more complex to support, and so I counted it as out of scope. We can discuss it in the future when we've got more time to review APIs and a concrete need for it. I do try and minimize the API surface overall, even though it's a lot.
Okay. Assuming You know that Imo and Stefan are still here. That them not saying anything means they have no feedback. Moving on to Trig. I assume there's nothing special here.
Yep, nothing special. The most interesting one there is sine cos because it returns a tuple just like the underlying one, but that tuple is a tuple of tensors for the allocating one, and it would end up so the ones that return tensor span, it returns a tuple. So instead of returning ref read only, that should actually, with the changes we've made, that should be a tuple of tensor span sine tensor span cos instead of ref read only tensor span.
Okay. Well, once I do the bulk copy and insert of this, I'll clean that one up.
Yeah.
And then negate.
So that's all the APIs for mirroring tensor primitives that we've already. Yep.
All right. Where was the copy button up here? Copy.
And the annotations for in and scoped should be all correct there, with scoped being applied when we return a span and we know that it won't capture that one in particular. So the inputs are scoped, the destination is unscoped. And then the compiler knows how to handle that when the input and the destination are the same already.
All right. So
This, yeah.
okay. So it's you're saying it here, and then we'll see the same thing popping in down here. I'll just start with why
Yep.
were these missed?
Yeah, so for it's just, you know, we had lots of APIs that were covered for tensor primitives. There was a handful that we missed. We've done reviews, like we actually went back and reviewed and approved, I think it was max magnitude numbers, since we got all the other max overloads and we had missed that one. These are ones where going through the set of APIs, some of these are ones that we have exposed since the initial tensor primitives work. So like the convert to integer and convert to integer native, those are new in net 9, so they weren't included in the initial concept for tensor primitives in 8. Decrement and increment, those ones are convenience ones where the one is implied. They aren't strictly needed, but they do achieve parity with the generic math interfaces. Clamp is also one of those newer ones where it exists as kind of min-max, but with specific behavior, and we optimized it for floating point. And so that these are kind of just all of the they exist, and they just weren't part of the initial proposal because of the size and overall scope of everything. And so this is completing it out and making sure we have the parity that we've decided exists across scalar and vector so far, and so should exist for tensor as well.
Okay. That in's not even legal, right?
I don't think so. I don't know how it would.
Yeah,
do
that should just be tensor cause.
Yeah.
Clearly, there was a find and replace, comma t with comma nt at some point. Okay. Just
Yes.
while doing the inline replacements, it
Yes, there
was like
was.
one of these lines was not like the other. So. Okay. So scrolling back down to this part. The equals is.
Yeah, so we've got bit decrement and bit increment, which get the next or lesser floating point value that compares greater than or less than the input. The first one shouldn't be decrement operators. It should be floating point IEEE 754. That's a copy paste accident. The clamp overloads, which take the X, the min, and the max that they're being clamped to. Did someone say something?
Sorry, I was breathing heavily at that moment.
Okay. No worries. We've got the convert to integer and convert to integer native. That those were new in net 9. Those are part of the. We opted to normalize floating point to integer conversion behavior so that it is consistent across all platforms. And so these ones give you access to. Here's the conversion to integer, explicit conversion, does what you expect, and then here's the one that does the native behavior and therefore is fast, but is not deterministic. So you just have the choice of, do I want something that is stable, or do I want something that is fast, depending on what's appropriate for them. And API Review opted for the name native there. I had originally brought it forward as, I think, estimate or unsafe to match our other APIs, and we opted for native instead. So
Emo, I think a mic just kicked on for you, and it has a weird hiss that it didn't used to have. That's better.
We then have divrem. That one's got the same issue where it's in tensor. It should just be tensor. And then the ones that return that take the destination buffers instead of void, that should be tensor span quotient, tensor span remainder.
All right. Remind me back up here. You said bit decrement should be not I decrement operator, but something else.
It should be I floating point IEEE 754. I've got that on the second, on the destination taking one, but not the tensor returning one.
Gotcha.
Yeah. We then have decrement and increment. Now, the decrement and increment are the only two here that I would say that if we really wanted to, we could just like exclude them because the functionality is already there via add x1, and you can just pass in the 1 as a scalar. They're here for mostly for parity with the generic math interfaces and everything else, so that there's a consistent, we've got it here, have it here. So you've got scalar vectors and tensors all being consistent between themselves. But they are a case where they are not actually strictly required. And I wanted to call that out explicitly.
I mean, it feels like we're saying these are big numbers. They should have the same numberitude that the smaller numbers have. Like, at the size of this proposal, I don't think we care about 4 functions.
That's fair, but I still want to be explicit about it because I like to as much as there's a lot of API surface that gets exposed in some of the areas because it's kind of fundamental operations. I don't like exposing more than necessary when we can trivially avoid it. So I wanted to make sure it was explicitly called out as like, we're doing this for consistency. If there is pushback, it is fine to drop them. We then have mean. Now, mean is an interesting case where it exists for tensors. It doesn't exist for scalars because you can't have the mean of a scalar, and we don't currently have it for vectors. Um, there probably needs to be a separate proposal for adding it to the vector types, but that's not critical for today. Um, uh, but mean is one that is prominent in all of the ML learnings, and so it's needed for tensor in particular. So I just wanted to call that one out as it and standard deviation are ones that only exist on tensors with this proposal, and they don't exist on scalars or vectors. And they can't exist for scalars because they're nonsensical there.
And
Or
and
no
this
op,
is
rather.
so if you have a tensor span of double, this is the supposed to be the perfect precision mean across 4 billion elements, then reduced back to double.
Yeah, it does. There's some tricks it does to optimize and keep things efficient, but it is the mathematical mean. Uh, the typical a better name for this might just be um uh might be average. But there's some specific connotations that differ between the statistical mean and the arithmetic mean. And mean is the more typical name in the machine learning space for what this API in particular is doing, even though they're sensibly essentially both the average.
Like I say, we did on link we called it average. I don't see a function
Yeah.
named mean anywhere.
Yeah, and I don't recall off the top of my head the exact difference between the arithmetic mean, which is average, and the mean that's being used here. And Michael's on vacation, unfortunately. He did remember what that was, so I'd be fine with marking this one as like, let's double check if it could be named average. But I recall there being a reason why, because I had raised the same point. I just don't have it in my notes as to what that was.
All right, I'm just going to say mean has been removed from this proposal, and it needs to come back with a discussion. So that we can approve everything except, it.
Yep.
Because if we need to call
And
it
then
statistical
for
mean so
standard
people
deviation,
know it's not the normal arithmetic mean and whatever that means, then we might debate between statistical mean and just calling it average anyway. And so I just want to make sure we actually have a representative audience when we discuss that.
Mm-hmm. Yep. For standard deviation, I imagine that there was going to be a comment as to the abbreviation here. The reason it's STD DEV instead of spelled out as standard deviation is because, much like square root, cosine, and other scenarios, the abbreviated form is the standard mathematical terminology used, and for the math functions, we have typically fit that terminology, particularly where calculators such as Wolfram Alpha or the TI graphing calculator specifically recognize the abbreviated form and not the elongated form.
I 100% would have believed we already had a std div name, but apparently we don't. System data entity core already has standard deviation spelled out. So, and system data entity DB functions has standard deviation spelled out. So system data entity has suggested that we're spelling it out. Fight. So this is Imo, Stefan, do you have opinions here on whether this is the
I
place
like this shorten.
to introduce div?
Do it.
Yeah, same.
All right. So I'll take a note that we already have some standard functions.
I'm mostly for it just because of where it lives, to be honest. Like, I might make a different decision in a different API, but when it's living next to things like divrem and SignPy.
All right.
and
Just-
POW.
Noting that we've previously expanded the concept, but that we accepted the small name here. So. All right.
The
and then,
next set here, I explicitly called out, but I didn't spell it all out. So we have a number of APIs that allow you to query information about the underlying. It allows you to query properties about the underlying numbers. Much like the relational operators, they return bool, and therefore would have the tensor of bool, the all, and the any overloads. There's also a proposal that's pending that's for exposing these on the vector types as well, because they're very much needed there. I figured one, didn't need to spell it all out to get them approved, because I couldn't fit them into the length, but that the discussion point would probably be around whether the prefix is appropriate, given the it's doing it across many. I didn't have a alternative prefix that immediately came to mind as better, however.
well, definitely in my mind, you can't mix is and any. Like, you can say adding tensor.isPow2, that the reason it's is instead of are is you're doing an element wise. But once you do the any or all reduction, then now you've accepted the notion that it's plural and you can't use is, you have to use are. Or we come up with a different prefix.
Yeah.
What would isPow2 represent here? Is it that, like, everything is a power of 2? Is it all? Or... like, element-wise?
Well,
Sorry.
so the one that so the ones that return a tensor of bool are element wise. So just like greater than, they return a tensor of bool, and it's doing the isPow2 operation on every single individual element. The ones that are suffixed with any and all do the operation per element, but they are allowed to short circuit. So if for all, it's basically saying are all elements in the input a power of 2, and if any of them are not, it returns false. And any says are any of these power of 2, and if any of them are true, it returns true. With greater than and greater than all, it kind of flows, like, not well, but it does flow that you can kind of suffix. But with, and more ideally, we probably would have called them like are all pow2 or are all greater than, and are any greater than, maybe.
So
or
if you
maybe
really
just all
wanted
greater
to,
than instead of having it as a suffix, but we didn't do that with the relational. So
Yeah, but they didn't.
right, for like
They don't
greater
have the
than and
is.
stuff.
So
Yeah,
'Cause-
we didn't do like, because you could do like element wise
Right.
is POW2, but then why didn't we do element wise greater than or whatever?
because basically
yeah, it's
it's that.
it's a little bit of a there's yeah. What if we just called it all POW2 and any POW2? Do we need
And then
the
what-
R there?
I mean, I think using our normal using normal English rules and normal BCL rules, I think we can drop the R's. It is
Yeah.
weird. I think that's the gesture. Yeah. Um, it is unfortunate that for
Although from the other side, using R instead of is nice.
yeah, I was gonna say the problem is no matter what we can't have them grouped unless we drop the is off of the is or we accept the is on the wides. And I really don't like accepting the is on the wides. Sorry, on the narrowing operation.
Hmm.
Because while there are some things where you can say you're talking about like a collection and is it all POW2 items, and you're like, okay, that means the all went to items and there's a second noun, but we don't really have a noun here.
You could do is all POW2 and is any POW2, but that still inserts a suffix between the two,
Yeah.
or inserts a word between the two instead of after.
And is any is weird because it would be has any. This so says my neural net of English. um, Chat suggests each any and or each all in any, but
Then we have to go back and add each to like all of our
that
other APIs. I feel.
yeah. While each slash all slash any looked fine in the suggestion, I don't like it once it's written out in the showing the function.
I mean, you could conceive of a world where you go back and like do a prefix that's common for element wise, any and all, and instead of ending, we start with it.
Well, because the each suffix works fine. Well, actually, no, because that that feels like it's POW2ing each element. That would be the other POW2. So.
Yeah.
Yeah, and if you did like is each POW2, it would almost sound like is all.
Yeah, so I don't know that there's a real difference between is and is each.
Or are each, yeah, but like each sounds like all too. You
Yeah,
kind of
and-
want element wise.
I think for the main one that returns the element wise, I think having it parity the scalar API is goodness there.
Yep.
I'm less concerned with the all and the any because they are specific to the tensor and vector variants, and for vector in particular, we can actually exclude them because you can efficiently do an any and all comparison without needing to worry about evaluation semantics because it's a primitive still. It's a type of scalar even if it's a multiple elements within one unit. But for tensor, we do need to have the all and any variants, and I don't have a strong preference for if we want to deviate here, if we want to call them all POW2 or is all POW2 or are all POW2. So I don't have a strong preference on what we decide there for the all and any for these variants.
I'm looking to see if we have any functions that are all followed by something. I see get alls, but
What if we did all is POW2 and any is POW2? Which would kind of flow with if we had it as a link API of all and any, and then a link API of is POW2 effectively. It composes in that way of how you'd write all over the comparison predicate you're doing. So it's just moving it from a suffix to a prefix.
That's the part I don't like, though. Like, why? Just because of the word "is," we move it from the suffix to the prefix. Like, why not be consistent?
Because
I mean,
that's bad English. And that's
yeah, at least
we applied a
not
formula,
even.
but good God.
But at least we're not trying to be English and failing. Like, this is just applying the pattern. Because I know this is what you originally proposed, Tanner. So I'm sure you're okay with it. Like, honestly, it's better than the alternatives that I've seen.
Yeah, I mean, we would lose the function
I'm
grouping
okay
of the
with it
suffix.
in that I would accept it.
So we would lose the function
Yeah.
grouping
I'm
of the
okay with
suffix,
it
but
in-
I think I like this one the best.
All PAL2 and any PAL2, and then
So our
what about
I think readability.
I think our pattern. So the pattern would be if that is turns into all or any when it's doing this form of Boolean reduction. Was denkst du,
I would
Immo?
also
Yeah.
I would also be fine with just switching all of these is's to r's and then applying the pattern, right? So like r PAL2, r PAL2 all, r PAL2 any.
Well, the downside of that is that it's then inconsistent with the scalar API.
Yeah. But like the scalar API doesn't have all or any anyway. But in the scalar API returns bools, not like tensors of bools for the non all and any. So it's like it's already different. But like I don't mind is necessarily because by sticking with is it kind of shows that we're not trying to be correct with our English and we're just applying a pattern. But yeah.
Yeah. So the each that was suggested, if we're turning is into r, then I mean, like this is bad English, right?
It is bad English. With the each at the end in particular.
Right.
Like
our
PAL2
our
all
POW2
is
each, because really it's our each POW2, and our all POW2 and our any POW2, and it's the I mean sometimes yeah. So we do the any suffixes and but when you say greater than any in y, it's like oh okay that makes sense. And amusingly, especially because your y was declared as an in ref, then you actually read x greater than any in y. But the
so like as far as grammatical English, like our each PAL2, our all PAL2, our any PAL2 is certainly the best. One couple problems that I have there. One is our each PAL2 and our all PAL2 kind of sound like the same thing, like depending on your interpretation. The other thing, like element wise, would be more clear, but again, like super wordy, and it just doesn't match what we're doing for any of the any of the methods that compare to something else. So it's like
yeah, I mean I think my inclination, especially with Immo having gone dark and we're at minimal quorum as it is, I think the answer is we punt all these to the future when we have more people to talk about it. Like we're already punting mean, so I think we can say that we have enough people to say standard dev is okay, but we need to figure out what the pattern is going to be on these is's and each's and alls and So I think that's just going to be a different discussion
And
that's itself going to take
from
40
all
minutes.
the suggestions, I think
Go ahead, Tanner.
from all of the proposals and suggestions so far, what I've come to is that I think that is-pow2 needs to stay as is-pow2 for overall consistency with the scalar. I think that's very important, and I'd push very strongly on that. For the any and all variants, I think that there's a little bit more flexibility in what we decide. And grammatically, I like all POW2 and any POW2 the best. But as a close second, I think the consistency of is POW2 all and is POW2 any, even though it's not great, it's at least consistent, and so that's a close second. And honestly, if we were, resetting this, I might have said that, even for greater than, we should have called it any greater than and all greater than, but we're, I think, 10 years too late for that at this point. And that would have also fixed your other concern of the scalar comparison.
Yep.
So it's kind of like we're 10 years too late there, and we're already somewhat like, it doesn't necessarily make sense in the API, but it's a formulation. And so the formulation following here, even if it's not the best English, makes that a close second for me.
Yeah, that's why. But since basically with this we would be doing establishing of precedent, it's I think letting those of us who were here sleep on it, and B, getting Steve's opinion, and maybe we'll get better than minimum quorum and get some other discussion, maybe some other suggestions. So we're probably going to keep this one as is, but I think the best answer is just to say none of them are being marked as approved right now, and we'll just discuss the shape as a separate problem.
Yeah, and I kind of agree with Tanner though. Like a lot of these APIs are basically formulaic descriptions more than English. So as long as people know what the API does, I care a lot less about whether it forms a valid English phrase. But yeah, there are pros and cons to all of those.
So since we're at time, what I'll do is I will extract the is APIs, and then I think there's like basically 20 APIs, not counting overloads, that are down below, which are concepts unique to Tensor. I will extract those to a part 3
And
proposal. That way we can approve what we have reviewed. Yes, and mean. Yes, I want to not forget mean. So I'll extract those to a separate proposal, and then hopefully we can finish that next Thursday. That way we can land these for Net 9 still.
Next Thursday is the 4th of July.
Yeah, good point.
I don't plan on working on a paid holiday.
So whenever our next availability for review is. Yeah, well, whenever our next availability for review is then.
Tanner, is that like if we move this stuff to a part 3, is that it, or is there something else coming in Tensor that we still need to review?
No, this should be the last of what we're planning on shipping in .NET 9. the last 20 APIs are the concepts that are unique to Tensor, covering things like reshaping and other things which I expect there's going to be discussion around the names on, like squeeze, where there's probably a better name, and there's some alternatives that I have for those, but we'll need to have the discussions over what's the best name for .NET, since there's a kind of existing standard in other ecosystems, and we want something that balances that with what's right for .NET and makes sense to users. But
Yeah.
we'll be done with tensors after that.
And remind me, none of them are experimental, right? They're all stable APIs.
Right. The plan is to ship them as stable. There's still a potential. There's still a potential need for. We still have to make a final determination on whether we're going to mark them as experimental or not. The plan is currently not to do that, but we have to assess the overall risk, and how confident we are that we've got enough user feedback that it is covering all the needs and scenarios. And right now we're near that bar, but we need to make that final determination.
Yeah.
Still.
Yeah, I can go either way. I was just asking because if we say we mark it as experimental, I'd be cool with time boxing the next review to an hour to have some more time for the other stuff that also has to go in. But yeah. I mean, so far it looks pretty much like rinse and repeat of the tensor primitive. So, I mean, yeah, there's some variation because the shape here is different, but it's close enough.
Right. And that's why all of that was first. It's the next part. It's the final part in the proposal here that is not like anything we've reviewed so far. And that's where I think it's probably going to take another full 2 hours to go through those concepts, because there's names and there's going to be opinions on those names since they're kind of new names. So I think we could time box like the is API, and we could time box the corresponding vector APIs that would allow us to accelerate these properly to an hour. I don't think we could time box the APIs like broadcast, squeeze, create and fill Gaussian normal distribution. I don't think those would fit in an hour.
Squeeze is going to give Kevin API flashbacks.
Are we then good for today?
Yep. So I have the summary of changes we did is we got rid of the ref read only because it wouldn't work. At least we don't think it would work. But we got rid of it. We fixed some bad interface decals. We talked about the shift operations being per element and decided it's fine to leave them out for now. Mean was removed because we need to discuss mean versus statistical mean versus arithmetic mean versus average. And we approved std dev, and we explicitly didn't decide on what to do with the is functions. And that was 2 hours. Or I think this first item was itself 40 minutes. So.
Yeah.
All right. Did I miss anything that anybody remembers? All right.
Approved. All right. See you, everyone.
That saved, and then we'll see if the minutes bot is allowed to edit in the video link.
It was actually quite productive.
You say that like you were surprised. I'm inclined not to take this as an insult.
He's just saying it's productive because we rubber stamped most of his proposal. No.
The 40-minute discussion on the shape of
No,
of the
I'm just glad
destination
that we
writing one
didn't
was
get
useful.
stuck too much on naming. Yeah.
All right. So, right. So, next week, Tuesday, should be a normal week for us. So, we'll see you at our same .NET time on our same .NET channel. And Thursday will be a holiday for us. So, if anyone's here, that'll be a surprise because neither Mo nor I should start the stream, no matter who shows up to the meeting. That doesn't exist. So, um, so yeah, we'll see you. See you next week. Or sorry, see you next Tuesday. And Auf Wiedersehen.
Auf Wiedersehen.